Hello everyone, I am Sixun Huang from National Kaohsiung University of Science and Technology, Taiwan. This video focuses on TCN, which stands for Temporal Convolutional Network. TCN was proposed by Bei and published in 2018. The outline of this video includes introduction about the motivation, central idea, and the architecture overview of the TCN, 1D dilated convolution, about the definition, and the pending rule of convolutional process in TCN, residual block, about two components in a residual block, dilated convolution layer, and the residual shortcut, and the setting of the residual block for achieving long memory. Sequence modeling is an essential task in many areas, such as weather and stock price prediction. Given an input sequence S0, S1 to ST, the goal of sequence modeling is to predict Y0, Y1 to YT sequentially. For the input S0, it predicts Y0. For given the next input S1, it predicts Y1. Input S2 predicts Y2, and so on. According to such formulation, sequence modeling task has two properties. The first one is causal constraint, indicating that the prediction of YT relies only on the path S0, S1 to ST, and not on feature ST plus 1 or ST plus 2. The second one is length constraint, meaning that the length of the output sequence is the same as the input sequence. Generally, recurrent networks are considered as the go-to solution for sequence modeling tasks. You can check out our YouTube channel or follow this link to watch a video about recurrent networks. Nevertheless, convolutional networks have recently achieved significant success in various applications. This prompts the question, can convolutional networks be extended to handle sequence modeling tasks? Accordingly, the central idea of TCN is to distill the design in the convolutional network to a simple network for sequence modeling. Initially, it employs 1D dilated convolution with zero pending to satisfy the causal and length constraints simultaneously. Additionally, it integrates the widely used residual shortcut from CNN, enabling the construction of very deep networks to extract effective features. To be more precise, a TCN that sequentially outputs Y0, Y1 to YT is a stack of several TCN residual blocks. Each residual block consists of two convolutional layers with a residual shortcut. The convolution layer within the residual block performs the 1D dilated convolution for sequence data, in contrast to 2D convolution typically in CNN. Before we proceed, let's clarify the functionality of 1D dilated convolution. Consider X as an input sequence ranging from S0, S1 to ST with C channels, where each Si can be represented as a C-dimensional vector. For instance, when C is 2, Si is a 2-dimensional vector. Let W denote a kernel comprising k kernel elements from W0, W1 to WK-1. Given the kernel for convolution with input, the kernel's channel must match that of the input. In this scenario, with k is 3, there exists 3 kernel elements, each of which is a 2-dimensional vector. The dilated convolution of input sequence S by the kernel W can be defined as this equation, where D is the dilation vector, and the dot denotes the inner product. For a kernel size k is 3 and the dilation vector D is 2, the definition of 1D dilated convolution becomes this equation. According to this equation, the output S convolute W of 7 is the sum of W0.S7, W1.S5, 2 steps backward from S7, and S2.S3, 2 steps backward from S5. Likewise, S convolute W of 6 is the sum of inner products computed from X6, 2 steps backward to X2. This equation provided is for S convolute W of 5. And this is 1 corresponds to S convolute W of 4. However, following this pattern, there is no definition for the term S convolute W of 3. This violates the previously mentioned length constraint. To address this issue, k-1 times D0 vectors are added to meet the length constraint, ensuring that the dilated convolution operations remain well defined at all times. In the extreme scenario of t equal to 0, there are k-1 kernel elements without definition. To ensure undefined kernel elements become well defined, a total of k-1 times D0 vectors must be appended to meet the length constraint. Here is an example to elaborate on 1D dilated convolution. Consider an element input sequence X with 2 channels and a kernel with 3 elements. The 1D dilated convolution of W and X with D equal to 2 can be computed as follows. First of all, we append 4 0 vectors in the purpose of meeting the length constraint. The computation of S convolute W of 0 is expressed as this equation, which sums these 3 inner products with a stepped interval of 2 and results in the value of 1. Subsequently, advancing the kernel by 1 step, we calculate S convolute W of 1 using this equation, resulting in the value of 2. After moving the kernel to X7, we generate the output sequence of the S convolute W that matches the length of the input sequence. Having explained 1D dilated convolution, we will now delve into the TCN residual block. For an input sequence with a length of T and Cin channels, the TCN residual block aims to output sequence Y with the same length as S and Cout channels. Both Cin and Cout are user-defined hyperparameters. Here is an example with a sequence length of 8, Cin equal to 2, and Cout equal to 3. in TCN residual block, two 1D dilated convolution layers are used to approximate a residual sequence R, while a residual shortcut is used to resume the target sequence. The idea of the residual network is elaborated in our YouTube video entitled Deep Residual Network. The first 1D dilated convolution layer is to convert the number of channels Cin of the input sequence S to Cout. This layer uses Cout kernels in order to match the output channel, and each kernel has Cin channels to align with the input channels for convolution. In this example, the 1D dilated convolution layer uses 3 kernels with 2 channels for transformation. As mentioned before, applying 1 kernel to X produces a 1-channel output sequence whose length is the same as X. Similarly, applying 2 kernels yields an output sequence with 2 channels. In the end, after applying 3 kernels, we obtain an output sequence with 3 channels. The second 1D dilated convolution layer is to output the residual sequence R with Cout channels. In this layer, Cout kernels are used to align with the output channel, while the kernel's channel is also set to Cout to match the channels of the output sequence from the first layer for convolution. Following the pattern of the first layer, the second layer uses 3 kernels and applies 1 kernel, 2 kernels, and 3 kernels to result in a sequence R with 3 channels. The function of the residual shortcut is to bypass the convolution operation. When Cin equals to Cout, the identity shortcut is used, and it directly forwards the input sequence to output for addition operation. When Cin is not equal to Cout, the projection shortcut is used to adjust the input to match the channel number of the output for subsequent addition. For example, when Cin is 2 and Cout is 3, the projection shortcut converts the input to the sequence with 3 channels. The projection shortcut achieves channel mapping via 1D dilated convolution. To match output channels, the number of kernels used is equal to Cout. For matching input channels during convolution, the kernel channel is set to Cin. The kernel size is set to 1 for the purpose of channel mapping, but not feature iteration. In this example, we use 3 kernels and each with a kernel size of 1. As previously stated, 1 kernel yields 1 channel, 2 kernels yield 2 channels, and 3 kernels yield 3 channels. After explaining the functionality of the residual block, we delved into the determination of the dilation factor within the block, so as to make the TCN look very far into the past for prediction. This is called the long receptive field. The guideline is to set the dilation factors of the convolution layers within the residual blocks in an exponentially increasing manner relative to the depth of the network. In simpler terms, the dilation factor is set to 1 for the residual block at level 0, 2 for level 1, and so forth. Within this configuration, the TCN can attain an exponentially long receptive field. Here, we illustrate this concept with a 3-layer TCN. Let's assume the length of the input sequence is 16. As mentioned, the 1D dilated convolution within the residual block maintains the length constraint. Consequently, the output lengths of all residual blocks are all 16. For a convolution with a kernel size of 3, the output element Y15 depends on 3 specific blue elements due to a dilation factor of 4 at this level. Moreover, these 3 elements are determined by these elements from the output of the 0-level residual block. Thus, Y15 is influenced by elements in the input sequence approximately 16 steps away, corresponding to 2 the power of the dilation vector set in the final layer. In this video, we present the TCN, a 1D convolutional neural network designed for sequence modeling tasks. The TCN's residual block uses 1D dilated convolution with zero pending to meet caudal and length constraints. By setting dilation vectors to increase exponentially with network depth, the TCN achieves an exponentially long receptive field. Thanks for your listening and have a wonderful day.